Now let us see difference tables. We have three difference tables. One is for forward difference, next one backward difference table, and another is central difference table. Let us see forward difference table. Forward difference table. Let me consider a data of length 4 x versus f of x. Okay, length of the data x0, x1, x2, x3. What is the length? 0 to 3 means 4. Okay, and the corresponding function values f of x0 denoted by f0, f of x1 denoted by f1, f of x2 denoted by f2, and f of x3 denoted by f3. Okay, now what is the first difference? First forward difference, first order forward difference, delta f. What is delta f? Simply f of x plus h minus f of x. Okay, so in between these two you write this is delta f naught. What is delta f naught? f1 minus f naught. Similarly, this value is delta f1, f2 minus f1. This value is delta f2, f3 minus f2. Now coming to second order forward difference denoted by delta square f. Already I told you delta square of f of x is nothing but delta of f of x plus h minus f of x. First for delta f of x, forward minus the function value. So here also, here between, what is this delta square f naught value? Just for your idea, I am writing delta f1 minus delta f naught. Same logic here, delta square of f1 means what? Delta f2 minus delta f1. And the last one, this is third order forward difference, delta cube f. Delta cube f, what is that? Delta cube f naught. What is this? Is delta square f1 minus delta square f naught. That means delta square f1 minus delta square f naught. This is forward difference table. And the important point is what here? Let me make star. What is that? Note that the differences delta power k f naught, remember what is this? Delta power k, delta f naught, delta square f naught, delta cube f naught, and so on, lie on a straight line sloping downwards to the right, sloping downwards to the right. Okay, the table is up to here only. Okay, this is the note. That means let me draw this one. What is this? Delta power, this is f naught, delta f naught, delta square f naught, and delta cube f naught. These are lie on the straight line sloping down towards the right side. Okay, this is forward difference table. Coming to now, let us see backward difference table. Backward difference table. Let me consider same data of length 4, x0, x1, x2, x3. Corresponding function values f1, f2, and f3. Now, backward difference. First order backward difference. And what is the first order backward difference? F of x minus f of x minus h. Minus f of x minus h. That means if I want to write del f1, means write f1 and one step backward, f0, like this. Okay, this is backward difference. So the first forward difference, this right in between these two, what is this? Del f1, and this is del f2, and this is del f3. Okay, for your idea, I am writing this is f1 minus f0. Similarly del f2, similarly del f3. Now Second order backward difference. Second order backward difference, it is the difference between, this is del square f2. Del square f2 means del f2 minus del f1. Del f2 minus del f1. And what is this? Del square f3. Del square f3. Second order difference is over. Now coming to third order difference, del square f3. Now this is the difference between del cube, third order, del cube f3 is nothing but, what is the last one? Del square f3 minus del square f2. Okay, this is third one. And what is the note here? Star point note is what? The differences del power k f3, del power k f3, that means del f3, del square f3, del cube f3, like that, lie on a straight line, sloping upward, to the right, means what? Let me draw this one, this backside, f3, del f3, del square f3, and del cube f3. And the values on this straight line are useful in backward difference interpolation formula. That is why we are noting this straight line. Okay, and the next one is, next table is what? Central difference table. Central difference table. Okay, let me consider the same data, x versus f of x, x0, x1, x2, x3. Corresponding function values f0, f1, f2, f3. Okay, now what is the first central difference? Del f. First central difference, del f. And what is the meaning of del f? One can write del f as this is, after this I will explain clearly one more shortcut to write del f formula. And what is del f? This first one is del f 1 by 2. Del f 1 by 2 means what? This one, f not f this f1 and 0 plus 1 by 2, 1 plus 0 by 2. And similarly this is del f 2 plus 1, this 2 plus 1 by 2, what is that? 3 by 2. 2 plus 1 by 2 is what? 3 by 2. And next one, this value denoted by delta f 3 plus 2 by 2, what is that? 5 by 2. This is first order. Coming to second order del square f, right in between these two. This is del square of what? 3 by 2 plus 1 by 2 by 2. 3 by 2 plus 1 by 2 by 2. 3 by 2 plus 1 by 2, 4 by 2 means 2. 2 by 2 again, this is del square f1 you will get. 3 by 2 plus 1 by 2 whole by 2, that is 1. Next one, coming to this. Delta square of 5 by 2 plus 3 by 2. 8 by 2. 8 by 2 means 4. 4 by 2. 4 by 2, that is 2. 4 by 2, this is 2. Isn't it? Right? Del square f. And 1, 2, 3 values are here. 1, 2, 3 values are here. Let me consider one more data point also to explain this one clearly. F4. And this becomes what? Delta f 4 plus 3 by 2, that is 7 by 2. And coming to here, delta square of 7 plus 5, 12 by 2, 6. 6, and this becomes what? Delta square f3. And third central differences, third order central differences, delta cube is now this part. Is what? This one. What is this? Delta cube of 2 plus 1 by 2, 3 by 2. And this is what? Delta cube f 3 plus 2 by 2, that is 5 by 2. This is over. Third order is over. Now fourth order finite differences. Fourth order finite differences. What is this? Delta power 4, 5 by 2 plus 3 by 2, 8 by 2 means 4. 4 by 2, that is 2. 4 by 2, that is 2. This is central difference table. And what is the note here? Note is what? The differences delta power 2k f2. What is the delta power 2k? Means even order central differences of f2 lie on a horizontal line, okay. Let me draw that one. What is that? Even order f2 is here, right? Delta power 4 actually the middle రావాలి. This must be middle. This one, this line, this is the straight line. These central differences, delta square, delta power 4, if the length of the data is more, delta power 6, all these are lines on the straight line which is horizontal. Okay, see relations between operators. Just now I have shown what is the first one. Already we proved this. Delta is e minus 1. This is proved. Now section 1, del equal to 1 minus e to the power of minus 1. Del equal to 1 minus e to the power of minus 1. Proof. What is del f of x? What is del f of xi? Or one can write this is f of xi minus f of xi minus h, isn't it? So this can be written as f of xi minus e to the power of minus 1 of f of xi, correct? As per using shift operator definition. So I can write 1 minus e to the power of minus 1 of f of xi. Therefore what is del is nothing but, this del is nothing but 1 minus e to the power of minus 1. 1 minus e to the power of minus 1. Now another one, this is the main point. See, what is delta fi? Delta fi is nothing but f of xi plus h minus f of x, right? And okay, let me write here. And del fi plus 1 is what? F of xi plus h minus f of xi, isn't it, right? And one more central difference. Delta of fi plus of is what? As per the definition of central difference operator, what is this? Let me write here. What is delta of f of xi? What is this? F of xi plus h by 2 minus f of xi minus h by 2. This is the definition of central difference. Now in place of I, what is this? I plus of. Therefore f of xi, right, plus h by 2 plus h by 2. I plus of is nothing but xi plus h by 2 minus f of xi plus h by 2 minus h by 2. This part is this one, I plus of. Okay, so after simplifying this, what I am getting, let me write here. This is equal to f of xi plus h I will get, right, minus f of xi minus f of xi. Therefore delta fi is this part, delta fi minus 1 is same, and delta fi plus 1 half is also same. Therefore what is the conclusion? Delta of fi is equal to del of fi plus 1 is equal to delta of fi plus of, delta of I plus of. Okay, using this we can construct difference table, and we can correlate, we can identify the values as per, we can identify the values as per the difference operator. Okay, that is why in central difference table I have used this notation, okay, in calculation. Okay, right. Next one, after difference table there are some proofs are there. What is that? Next one, delta equal to e to the power of half minus e to the power of minus half. Okay, and the proof is already simple one. This is what is delta of f of xi. This is f of xi plus h by 2 minus f of xi minus h by 2, isn't it? So I can write this is e power 1 by 2 of f of xi plus h by 2 means, and minus h by 2 means e power minus of f of xi. So take common e power of minus e power minus of, and the common term is f of xi. Therefore now f of xi is over. Delta is nothing but this operator. Therefore delta equal to e power of minus e to the power of minus half. This is one more. And another one, coming to another one, what is that? Average operator. Mu equal to 1 by 2 e power half plus e power minus half, e power minus half. And coming to this proof, what is mu f of xi? Mu f of xi is 1 by 2, that is average of what? Xi plus h by 2 plus f of xi minus h by 2. Okay, so one can write this bracket as, in terms of shift operator, this is e power of f of xi plus this is e power minus of f of xi. Okay, so I can write this is 1 by 2 e power of plus e power minus of, what is the common? F of xi is common. So comparing the operators on both sides, so mu is equal to what? 1 by 2 e power 1 by 2 plus e power minus 1 by 2, e power minus 1 by 2, right? And the next one, take next one, delta equal to del into 1 minus del whole power minus half, whole power minus half. Proof. Let us consider RHS first. RHS del into 1 minus del whole power minus half. What is del? Is nothing but 1 minus e power minus 1, correct? Del formula. And let me substitute that one also here. 1 minus e power minus 1, 1 minus e power minus 1, this whole power minus half, right? So let me write here, this is equal to 1 minus e power minus 1, and here 1 gets cancelled, minus into minus plus e power 1 by 2 you will get, right? Whole power e power 1 by 2 you will get. Take this one inside, e power 1 by 2 minus e power minus 1 plus 1 by 2, that is equal to e power 1 by 2 minus e power minus 1 by 2, that is nothing but central difference operator. Now another one, mu equal to 1 plus delta square by 4 whole power 1 by 2, whole power 1 by 2. Proof by taking RHS. In RHS, what is the term? Delta square term is there. So what is actually delta in terms of shift operator? E power of e power minus half. This implies delta square is equal to what? E power of minus e power minus half whole square, whole square. So this is equal to a square plus b square minus 2ab, right? A square plus b square minus 2ab. Now 1 plus delta square by 4 equal to 1 plus e plus e power minus 1 minus 2 by 4, correct? Right? So that is equal to, if I take 4 LCM, 1 by 4, this is what? 4 plus e power minus 1 minus 2, that is equal to 1 by 4 e plus e power minus 1 plus 2, e power minus 1 plus 2. So that is equal to this is what? 1 plus delta square by 4 value 1 by 4 e power, I can write e power half plus e power minus half whole square, correct? Right? Now 1 plus delta square by 4, what is RHS? Whole power 1 by 2. So this is 1 by 2 of what? E power half plus e power minus half. This is nothing but average operator. This is nothing but average operator. Now consider one problem based on errors. Construct the difference table. Construct the difference table for the sequence of values f of x equal to 0 0 0 epsilon 0 0 0, where epsilon is an error. Epsilon is an error. Also show that first question, the error spreads and increase in magnitude as the order of differences is increased. Okay. And the second question, the errors in each column have binomial coefficients. Okay, this is the question. So solution. First, what is the function values are given? So let me draw the table first. F of x, what are the function values? 3 zeros, epsilon, 3 zeros, right? Let me draw the table, difference table, forward difference table or backward, whatever it is. I am considering forward. First, forward difference. What is the difference between this 0 and this 0? 0 right here. 0 minus 0, this is nothing but f0, f1, f2, f3, f4, f5 and f6. Now this is f1 minus f0. This is also in between 0. This is what? Epsilon minus 0 and 0 minus epsilon. 0 minus epsilon. Okay. And 0 minus 0 0, 0 minus 0 0, right? First order is over. Now coming to second order differences, delta square f0, difference between this and this right here, and epsilon minus 0 right here, epsilon minus 2 epsilon, and 0 minus epsilon plus, and this is 0, right? And coming to third, delta q, epsilon minus 0, epsilon minus 2 epsilon minus 3 epsilon, epsilon minus of minus 2 epsilon plus 3 epsilon, and this is minus epsilon. Coming to fourth order differences, minus 3 epsilon minus 4 epsilon, 3 epsilon plus 3 epsilon, 6 epsilon, and this is minus epsilon minus 3 epsilon, delta power 5. Fifth order forward difference, 6 epsilon minus of minus 4 epsilon, 10 epsilon, this becomes minus 10 epsilon, and delta power 6 f, last one, minus 10 epsilon, 20 epsilon, and this is the error table is over. See the first question, the error spreads. What is the first question? The error spreads and increase in magnitude as the order of the differences increased. What is the error actually here? Error is what? Epsilon, right? And when order increases, see what is the now last error? 20 epsilon. Error is spreading. Here only one error in the data. Now here there are 2 errors. Here there are 3 errors. Here 4 errors. Like that. Okay. So error is increasing. Error spreads. at each difference table and increase in magnitude. First it is epsilon only, then it is 2 epsilon. Forget about the sign because error is always taken in quantity. 3 epsilon is there, next 6 epsilon is there, next 10 epsilon is there, next 20 epsilon is there. So error is increasing in magnitude when the differences are increased, right? And next, second point, thus errors in column, the errors in each column have binomial coefficients. Error in each column have binomial coefficients. See, in second order, what are the terms? Epsilon, minus 2 epsilon, epsilon. Third order, epsilon, minus 3 epsilon, plus 3 epsilon, minus epsilon. Okay, these are binomial expansion of, okay, I will write in the next table. I will write. See, what is the first observation? The above table shows how the error affects the differences. How the error affects the differences. Error affects the differences. The second column, the second difference column, the second difference column has the errors. What are the errors? Epsilon, minus 2 epsilon, and epsilon. In third difference column, third difference column has errors. What? Epsilon, minus 3 epsilon, plus 3 epsilon, minus epsilon. And the fourth difference column has what errors? Fourth difference column is not sufficient to show all the expected errors. Fourth column, what are the errors actually? Previous table also, minus 4 epsilon, you write like this. The fourth column is not sufficient to show all of the expected, you write expected errors, all of the expected errors. What are the expected errors here? Epsilon, and fourth one, minus 4 epsilon is there, next 6 epsilon is there, next again minus 4 epsilon is there, and the next epsilon, last one epsilon. Okay, right. Second one epsilon epsilon, fourth one also epsilon epsilon, right? Okay, thus we may conclude that errors in each column have binomial coefficients. Errors in each column have binomial coefficients. Further, the maximum error occur. What is the maximum error? 20 epsilon occur directly opposite to entry, that is 20 epsilon is directly occur opposite to epsilon, the starting value of entry, where the function value is in error. Okay, this is the first point for this problem.